the speed of light isn't about light at all, and understanding this will change how you see everything. If the sun disappeared right now, you wouldn't know for 8 minutes. Darkness would arrive, not creeping in gradually like a sunset, but hitting all at once, like someone flipping a switch in a cosmic room, plunging everything into instantaneous night. But here's what they don't tell you in school, what gets lost in the physics classes and the equations. This isn't really about how fast light moves. This is the story of how we discovered that limit, what it really means, and why it might be the most important number in all of physics. For most of human history, we believed light was instant, that the moment a candle was lit or the sun rose, its illumination reached us without any passage of time whatsoever, spreading across space in a way that seemed to defy the concept of speed entirely. This seemed obvious. After all, when you flip a light switch, the room illuminates immediately, or at least appears to, with no perceptible delay between cause and effect. But appearance, as we would discover, can be profoundly deceiving when dealing with phenomena that operate at scales beyond our everyday experience. The first serious attempt to measure light speed came in 1638, when Galileo Galilei devised what seemed like a clever experiment involving 2 hilltops in the Tuscan countryside, separated by roughly a mile of rolling Italian landscape dotted with olive groves and vineyard. He stationed himself on one hilltop with a covered lantern, while his assistant took position on another hill with an identical setup, both waiting in the darkness of night for the experiment to begin. The plan was beautifully simple in concept. Galileo would uncover his lantern, allowing its light to flash across the distance, and the instant his assistant saw that flash, he would uncover his own lantern in response, creating a return signal that Galileo could observe. By measuring the total time between his action and seeing his assistant's light, then subtracting the known human reaction time, they should theoretically be able to calculate how long light took to travel that 2-mile round trip through the night air. The result was immediate disappointment. They measured nothing except human reaction time itself, the delay of nerves and muscles responding to visual stimulus. Light, if it had any travel time at all across such a short distance, was moving far too quickly for their 17th century equipment and methods to detect with any precision. Galileo concluded honestly that light was either infinitely fast or so close to infinite that the difference didn't matter for practical purposes, at least not over distances humans could easily create on Earth's surface. He had failed in his immediate goal, but his experiment planted something crucial in the scientific consciousness. The question itself, the idea that perhaps light's speed could be measured, that it might not be infinite after all. The breakthrough came 38 years later from an unexpected source, not from someone studying light directly, but from an astronomer watching Jupiter's moons with the kind of obsessive precision that only truly dedicated observers possess. Roemer, a Danish astronomer working at the Paris Observatory in 1676, had been assigned what seemed like a routine task, creating precise tables of when Io, Jupiter's innermost large moon, would disappear behind the giant planet in eclipse. This wasn't just academic curiosity. Accurate eclipse timing tables had practical value for navigation, as they provided a kind of cosmic clock that sailors could use to determine longitude at sea, a problem that had plagued maritime navigation for centuries. Roemer was meticulous, recording eclipse after eclipse with the best telescopes available, noting the exact moment when Io's pale disk vanished behind Jupiter's massive bulk, then reappeared on the other side roughly 42 hours later. But something bothered him, a pattern in his data that didn't make sense if you assumed, as everyone did, that light traveled instantaneously. The eclipses weren't happening when they should, when his mathematical predictions said they would occur based on Io's orbital mechanics. which were well understood and should have been perfectly predictable. In January, when Earth was closest to Jupiter in its orbit, Io's eclipses happened right on schedule, matching his predictions to within seconds. But in July, when Earth had moved to the opposite side of its orbit and was now much farther from Jupiter, the eclipses were running late, not by seconds, but by a full 16 minutes, a huge discrepancy that couldn't be explained by errors in observation or calculation. The pattern repeated with perfect consistency year after year. Early when Earth was approaching Jupiter, late when Earth was receding, with a maximum difference of 16 minutes occurring when Earth was at its farthest point from the giant planet. Roemer had what we might today call an aha moment, a flash of insight that reframed everything. The eclipses weren't actually happening at different times. They were happening exactly when the orbital mechanics predicted. But the light carrying the information about those eclipses had to travel different distances to reach Earth, depending on where our planet was in its orbit. When Earth was closer to Jupiter, light had less distance to cross, arriving sooner. When Earth was farther away, light had more distance to cover, arriving later, creating an apparent delay in the timing of events that were actually occurring with perfect regularity. This meant something revolutionary. Light had a finite speed, and that 16-minute maximum difference represented the time it took light to cross the additional distance of Earth's orbital diameter, roughly 300 million kilometers of empty space. Using this reasoning and the astronomical distances known at the time, Roemer calculated that light traveled at approximately 220,000 kilometers per second, which was remarkably close to the true value considering the limitations of 17th century astronomical measurements and the uncertainties in planetary distances. He was off by about 26%. But that didn't matter. What mattered was the principle, the proof that light wasn't instantaneous. That information took time to propagate through space. That the universe had a kind of cosmic speed limit governing how quickly news of distant events could reach observers. Over the next 2 centuries, scientists refined this measurement with increasingly clever experiments that didn't require astronomical distances or planetary observations. In 1849, French physicist Hippolyte Fizeau designed an apparatus that would have delighted Galileo with its mechanical ingenuity, a rapidly spinning cogwheel with 720 teeth around its circumference, rotated by a complex gear mechanism at 25,000 revolutions per minute, creating a blur of metal moving faster than the eye could follow. He directed a beam of light through a gap between 2 teeth, sent it racing 8 kilometers across the rooftops of Paris to a distant mirror on Montmartre, and captured it coming back through what should have been the same gap, except the wheel had rotated slightly during the light's journey, so the returning beam would either pass through the next gap or be blocked by the next tooth depending on the exact timing. By adjusting the rotation speed until the returning light was blocked, Fizeau could calculate precisely how long the light had taken to make its 16-kilometer round trip, and from that, derive its speed. His result? 315,000 kilometers per second, within 5% of the true value. A remarkable achievement using nothing but 19th century mechanical engineering and optical precision. Léon Foucault, famous for his pendulum demonstration of Earth's rotation, improved the method further by replacing the toothed wheel with a rotating mirror that deflected the returning light beam by a tiny angle. An angle that could be measured with extreme precision using the optical techniques of the day. His measurement in 1862 yielded 298,000 kilometers per second, so close to the actual value that the remaining uncertainty was mostly due to the difficulty of measuring the exact distances between mirrors and the precise rotation speed of his apparatus. By the late 1800s, thanks to the work of Albert Michelson, who would win America's first Nobel Prize in physics, partly for his measurements of light, We knew the speed with incredible precision, 792 kilometers per second, accurate to within a fraction of a percent. We had measured light's speed to extraordinary accuracy, refining our number through decades of increasingly sophisticated experiments. But here's what troubled the greatest minds of that era. We still didn't understand why light had this particular speed, why it wasn't faster or slower, why nature had apparently chosen this specific number out of all possible values. And even more mysteriously, we didn't know what this speed was measured relative to. After all, speed is usually defined as motion relative to something else, like a car moving at 60 kilometers per hour relative to the road, or Earth orbiting at 30 kilometers per second relative to the sun. So what was light moving relative to when we measured its speed? What was the reference frame? The answer to that question would require the most famous failed experiment in the history of science. In 1887, two American physicists, Albert Michelson and Edward Morley, built what was arguably the most sensitive scientific instrument that had ever existed up to that point in human history. A device so precise it could detect changes in the speed of light smaller than 1 part in 10,000. Variations so tiny they would be invisible to any less sophisticated apparatus. Their laboratory in Cleveland, Ohio, housed a massive stone slab floating on a pool of liquid mercury to eliminate vibrations from passing carriages or footsteps, supporting an arrangement of mirrors and beam splitters designed to compare light traveling in perpendicular directions with almost unimaginable precision. They weren't just trying to measure light speed more accurately. They were hunting for something far more fundamental, evidence of the luminiferous ether, the invisible substance that 19th century physics absolutely required to exist in order to make sense of how light could travel through the vacuum of space. The logic seemed airtight at the time. All known waves required a medium to propagate through. Sound waves needed air or water or solid matter. Ocean waves needed water. Vibrations needed something physical to vibrate. So light waves, which could cross the vast emptiness between stars, must therefore be oscillations in some incredibly subtle, all-pervasive medium that filled every cubic centimeter of space. This hypothetical substance, called the luminiferous ether, had to have remarkable properties, thin enough that planets could orbit through it without slowing down over thousands of years, yet rigid enough to transmit light waves at 300,000 kilometers per second, which required a stiffness exceeding that of steel by an enormous factor. But if the ether existed, and if Earth was plowing through it at 30 kilometers per second as our planet orbited the sun, then there should be an ether wind blowing past us, similar to the way you feel wind on your face when you stick your head out of a moving car window. Even on a perfectly calm day, light traveling through this ether, wind should behave like sound traveling through moving air, moving slightly faster when going with the wind, slightly slower when moving against it, with the difference depending on the ether's flow direction and speed relative to Earth. Michelson and Morley's apparatus was designed to detect exactly this effect by splitting a light beam into two perpendicular paths, sending each beam back and forth several times to amplify any tiny differences, then recombining them to create an interference pattern that would shift if one beam had traveled even slightly faster or slower than the other. They conducted their experiment carefully, rotating the entire apparatus to test light speed in every possible direction, taking measurements at different times of day and different seasons to account for Earth's changing motion through space as it orbited the sun and rotated on its axis. The expected result was clear. They should see the interference pattern shift as the apparatus rotated, revealing the direction and speed of Earth's motion through the ether, finally answering one of the great questions of 19th century physics. The actual result was stunning in its simplicity and deeply troubling in its implications. Nothing, Absolutely nothing. No shift whatsoever in the interference pattern, no matter which direction they pointed their apparatus. No matter what time of day or what season of the year, light traveled at exactly the same speed in all directions, completely independent of Earth's motion through space, as if the ether wind didn't exist, or as if Earth was somehow always stationary relative to the ether, despite obviously hurtling through space at enormous speeds. This made no sense according to the physics of the time, violating every intuition about how motion and velocities should combine. It was like being on a train traveling at 100 kilometers per hour, throwing a ball forward at 20 kilometers per hour, and measuring the ball's speed relative to the ground as still only 20 kilometers per hour instead of the expected 120. Think about what this means in practical terms. You're standing on a platform, perfectly still, and you measure light from a flashlight traveling at exactly 300,000 kilometers per second, which seems reasonable enough. Now you get on a train moving at 200 kilometers per hour, not anywhere near light speed, but definitely moving, and you shine the same flashlight in the direction of the train's motion, sending light racing ahead down the tracks. Common sense, backed by centuries of studying how velocities add together, says that light should now be moving at 300,000 kilometers per second plus 200 kilometers per hour relative to the platform you just left. The light's original speed plus the train's contribution. But when you actually measure it, using equipment sensitive enough to detect such differences, the light is still moving at exactly 300,000 kilometers per second relative to the platform, as if the train's motion contributed nothing whatsoever to the light's velocity, as if the universe was somehow compensating to keep light's speed constant. And here's what made it even stranger. Someone standing on the platform, watching your train pass by, also measures your flashlight's light traveling at exactly 300,000 kilometers per second relative to themselves, not relative to the train. The same light beam has the same speed for both of you, despite you moving relative to each other, which should be impossible if velocities add the way we thought they did. The Michelson-Morley experiment failed completely in its stated goal of detecting the ether, but in failing, it discovered something far more profound. Light speed is absolute, invariant, the same for every observer, regardless of their motion or the motion of the light source. A universal constant that refuses to change, no matter how you try to manipulate the conditions of measurement. Scientists spent years trying to explain this away, proposing increasingly elaborate theories to save the ether concept. Maybe Earth was somehow dragging a bubble of ether along with it. Maybe the ether had some special property that coincidentally cancelled out the expected effects. Maybe the experimental apparatus was contracting in the direction of motion in just such a way as to hide the real results. But all these explanations felt forced, ad hoc, like patching holes in a theory that was fundamentally flawed, rather than accepting what the evidence was trying to tell them. The answer, when it finally came, would require abandoning some of the most basic assumptions about reality that humans had held since the dawn of conscious thought. The ideas that time flows at the same rate for everyone, that space has a fixed, unchanging geometry, that the past and future are absolutely defined concepts, independent of an observer's motion. A young patent clerk in Switzerland, with no access to fancy laboratory equipment, no prestigious academic position, not even a doctorate degree at the time, was about to overturn everything we thought we knew about the structure of the universe. At the age of 16, while still a student struggling with the rigid educational system of late 19th century Germany, Albert Einstein asked himself a deceptively simple question that would haunt him for the next 10 years. What would you see if you could travel alongside a beam of light, moving at the same speed as the light itself, racing through space at 300,000 kilometers per second? The answer seemed obvious at first glance. You should see the light waves frozen in space around you. A static pattern of oscillating electric and magnetic fields suspended in time like a photograph of a water wave captured at the perfect instant. Neither advancing nor receding, but simply existing as a stationary pattern in the void. But something troubled Einstein about this image. A deep inconsistency that gnawed at his physicist's intuition. Even as a teenage student, James Clerk, Maxwell's equations describing electromagnetic waves, the mathematical framework that had united electricity, magnetism, and light into a single coherent theory just decades earlier, contained no solution for a stationary light wave, no mathematical possibility for a frozen electromagnetic field pattern. The equations insisted that electromagnetic waves must propagate, must move through space at a specific speed, determined by the electric and magnetic properties of the vacuum itself, a speed that turned out to be exactly the measured speed of light, which is how Maxwell had realized that light itself was an electromagnetic phenomenon in the first place. So here was the paradox that wouldn't leave him alone. If you moved alongside light at light speed, you should see a stationary wave according to simple addition of velocities. But Maxwell's equations said such a thing couldn't exist, creating a fundamental contradiction at the heart of physics. For 10 years, Einstein turned this problem over in his mind, thinking about it during his studies at the Swiss Federal Polytechnic, contemplating it during his job search after graduation when no university would offer him an academic position, puzzling over it during his work at the Bern Patent Office, where he evaluated applications for electromagnetic devices more relevant to his future breakthrough, systems for synchronizing clocks across railway networks. That work with clock synchronization turned out to be more than just a day job. It planted seeds about the fundamental nature of time, about how we define simultaneity, about what it really means to say that two events happen at the same time when those events occur in different places. The breakthrough came in 1905, Einstein's miracle year, when the 26-year-old patent clerk published 4 papers that would revolutionize physics, each one worthy of a Nobel Prize on its own merits, addressing the photoelectric effect, Brownian motion, special relativity, and the equivalence of mass and energy. The relativity paper, titled with characteristic directness on the electrodynamics of moving bodies, started from a radical premise. What if the problem wasn't with Maxwell's equations but with our assumptions about space and time themselves? What if, instead of trying to make light's behavior fit our intuitions about how motion should work, we accepted light's constant speed as a fundamental principle and rebuilt our understanding of space and time to accommodate it? Einstein proposed 2 simple postulates that would demolish and rebuild the foundations of physics. First, the laws of physics are the same in all inertial reference frames moving at constant velocity. There's no absolute state of rest, no privileged perspective from which to measure motion. Second, the speed of light in vacuum is the same for all observers, regardless of their motion or the motion of the light source. That second postulate directly contradicted common sense and everyday experience, where velocities add together in the simple, intuitive way. A ball thrown forward from a moving train has its velocity added to the train's velocity when measured from the ground. But Einstein was saying light doesn't work this way. Shine a flashlight forward from that train, and the light still travels at exactly 300,000 kilometers per second relative to the ground. Not that speed plus the train's velocity. As if the universe was enforcing an absolute speed limit that couldn't be exceeded or even approached through simple addition. The consequences of accepting these postulates were staggering and deeply counterintuitive, requiring a complete reimagining of concepts humans had thought were absolute and unchanging since time immemorial. Time, Einstein showed through rigorous mathematical derivation, is not absolute. It doesn't flow at the same rate for everyone, everywhere. like some cosmic metronome, ticking away the same seconds for all observers throughout the universe. Instead, time is relative to motion. If you move very fast relative to someone else, time literally flows more slowly for you compared to them. An effect called time dilation that becomes more pronounced as you approach light speed. This isn't just a matter of clocks malfunctioning or appearing to run slow. Time itself, the actual rate at which physical processes occur, chemical reactions happen, particles decay, slows down for objects in motion relative to a stationary observer. The mathematics gave a precise formula for this effect. At 90% of light speed, your time runs at only about 43% of the rate experienced by someone standing still. For every hour that passes for you, 2.25 hours pass for them. A difference dramatic enough to notice even in human lifespans. At 99% of light speed, the effect becomes even more extreme. Your time crawls at about 14% of the stationary observer's rate. Your 1 year equals their 7 years, aging you dramatically less over the same journey through space. And as you approach ever closer to light speed, 99.9%, 99.99%, time dilation becomes more and more severe, stretching toward infinity as you reach the speed of light itself. At which point, theoretically, no time would pass at all for the traveler. Space itself isn't spared from this revolution. Einstein showed that objects contract along their direction of motion when moving at high speeds, a phenomenon called length contraction that becomes noticeable at relativistic velocities. A spaceship 100 meters long when at rest would shrink to about 43 meters in the direction of motion when traveling at 90% light speed, as measured by a stationary observer, while the astronauts inside experience their ship as perfectly normal length, but see the outside universe compressed in the direction of travel. This isn't an optical illusion or a measurement error. The contraction is real, a genuine change in the geometry of space itself that emerges from the requirement that light speed remain constant for all observers. Here's where it gets even more mind-bending. Simultaneity. The concept of events happening at the same time is also relative, not absolute. Two events that occur simultaneously, according to one observer, might happen at different times, according to another observer, moving relative to the first, with no way to say who's really right, because there is no absolute reference frame, no cosmic arbiter of what constitutes now across the universe. This means that the present moment, the now you're experiencing, exists only in your immediate vicinity. There is no universal present moment shared across the cosmos. No meaningful way to point at a distant galaxy and say, this is what's happening there right now, because right now depends on your motion relative to that galaxy. We see these effects not just in thought experiments, but in actual, measurable phenomena that modern technology has to account for to function properly. GPS satellites orbiting Earth are moving fast. Not anywhere near light speed, but fast enough that time dilation becomes significant at the precision required for accurate navigation that we take for granted every day when using our phones to get directions. These satellites orbit at about 14,000 kilometers per hour while experiencing weaker gravity than we do on Earth's surface. And both effects influence how fast time passes for them compared to us. Special relativity says their motion should make their clocks run slightly slower than ours, about 7 microseconds per day, slower due to their velocity through space. But general relativity, Einstein's later theory incorporating gravity, says that because they're farther from Earth's center and experiencing weaker gravitational pull, their clocks should run faster than ours, about 45 microseconds per day faster due to the gravitational time dilation effect. The net result: satellite clocks run about 38 microseconds per day faster than clocks on the ground. And if we didn't correct for this relativistic effect, GPS coordinates would drift by about 10 kilometers per day, making navigation systems useless within hours. Every time you check your location on your phone and it correctly shows you standing on the right street corner, you're experiencing proof that Einstein was right about time dilation. That it's not just theory but measurable reality that engineers have to compensate for in practical technology. There's even more dramatic evidence from cosmic rays, high-energy particles from space that slam into Earth's upper atmosphere at near light speed, creating showers of secondary particles, including ones called muons, that rain down to ground level constantly. Passing through your body by the thousands every second, muons are unstable particles with an average lifetime of just 2.2 microseconds before they decay into other particles. Blink, and they're gone, existing for such a brief moment that you'd think they couldn't possibly travel very far before vanishing. At near light speed, even moving at 99.9% of the speed of light, a muon should only travel about 600 meters during its 2 microsecond lifetime before decaying. Simple multiplication of speed times time, but these muons are created about 15 kilometers up in the atmosphere when cosmic rays hit air molecules. And yet they reach the ground in large numbers, detectable by equipment at sea level, traveling 25 times farther than they should be able to before their built-in death clock runs out. How is this possible? Time dilation provides the answer. And it does so in a way that beautifully illustrates the relativity of the phenomenon. From the muon's perspective, racing downward at near light speed, time is flowing normally. It experiences its full 2.2 microseconds of existence. No more, no less, ticking away according to its internal physical processes. But the atmosphere in the muon's reference frame is compressed, squashed by length contraction from 15 kilometers down to about 600 meters, short enough that the particle can traverse it in its brief lifetime. The entire thickness of our life-sustaining blanket of air reduced to a thin film from the muon's perspective. From Earth's perspective, standing still on the ground, looking up, the atmosphere has its normal thickness of 15 kilometers. Not contracted at all, because we're not the ones moving at relativistic speed, but the muon's internal clock is running slow due to time dilation. Instead of lasting only 2 microseconds by our watches, the muon persists for about 50 microseconds from our viewpoint, stretched by a factor of 25 due to its extreme velocity, giving it plenty of time to complete the 15-kilometer journey before decaying. Same physical phenomenon. Two completely different but equally valid descriptions, depending on your reference frame. From one view, space contracts but time is normal. From the other view, time dilates but space is normal. Yet both perspectives agree on the final outcome that muons reach the ground. This is what Einstein meant by relativity. Not that everything is arbitrary or subjective, but that different observers, moving relative to each other, will measure different values for time intervals and spatial distances, while still agreeing on the underlying physics and on quantities that combine space and time. In particular, ways, but the deepest, most profound consequence of Einstein's theory came from a different line of reasoning, one that would lead to the most famous equation in all of physics, and reveal why the speed of light truly is an absolute limit that can never be exceeded by anything with mass. In September of 1905, just months after publishing his paper on special relativity, Einstein submitted a brief 3-page addendum that contained perhaps the most consequential insight in the history of science, a realization that would eventually lead to nuclear power, atomic weapons, our understanding of how stars shine, and a fundamental explanation for why nothing with mass can ever reach the speed of light. The paper was titled, "With Einstein's Characteristic Modesty, Does the Inertia of a Body Depend on its Energy Content?" And it introduced an idea so revolutionary that even Einstein himself didn't immediately grasp all its implications. Energy and mass are equivalent. two manifestations of the same underlying quantity, interconvertible through a simple mathematical relationship. That relationship is expressed in what has become the most recognized equation in human culture. Energy equals mass times the speed of light squared. A formula so famous that it appears on t-shirts and coffee mugs, usually written in its abbreviated form that hides the profound strangeness of what it's actually saying about the nature of reality. Let's unpack what this equation really means, starting with that speed of light squared term, which is an almost unimaginably large number, 300,000 kilometers per second, multiplied by itself, giving 90 trillion meters squared per second squared. A conversion factor between mass and energy that reveals just how much energy is locked inside even tiny amounts of matter. 1 gram of matter, about the mass of a paperclip, contains 90 trillion joules of energy, which is roughly equivalent to the explosive yield of the atomic bomb that destroyed Hiroshima, or enough electricity to power a typical American home for over 2,000 years. Your body, assuming you weigh around 60 kilograms, contains approximately 5 quadrillion joules of energy, equivalent to about 1,200 Hiroshima bombs worth of destructive potential. Enough energy to power the entire United States for several hours, if it could somehow be completely converted to usable form. This isn't just a theoretical curiosity. We can see this equivalence in action every time we look at the sun, that familiar yellow disk that provides essentially all the energy for life on Earth, shining through a process that converts mass directly into radiation according to Einstein's equation. Deep in the sun's core, where temperatures reach 15 million degrees and pressure is so intense that matter is squeezed to densities over 100 times that of water, hydrogen nuclei are being fused together into helium through a complex series of quantum mechanical reactions that only become possible under such extreme conditions. Each fusion event converts a tiny fraction of the initial mass into energy. About 0.7% of the hydrogen's mass vanishes, transformed into gamma rays and other particles that carry away energy according to that famous equation. This doesn't sound like much, less than 1%. But when you're fusing about 600 million tons of hydrogen every single second, that tiny percentage adds up. 4 million tons of the sun's mass simply ceases to exist every second, converted entirely into the light and heat that warm our planet and make life possible. 4 million tons every second, gone, transformed into pure energy. Yet the sun is so massive, about 2,000 trillion tons total, that it can sustain this prodigious rate of mass loss for another 5 billion years before exhausting its hydrogen fuel. The sun is literally getting lighter as you listen to this, losing mass with every photon it radiates, though you'd never notice because the percentage change over a human lifetime is infinitesimal, far too small to affect the gravitational pull that keeps Earth in its orbit. But here's where the equivalence between mass and energy reveals something crucial about the speed of light as a cosmic limit. If mass and energy are interchangeable, then adding energy to an object doesn't just make it move faster. At high speeds, it also makes it more massive, increasing its resistance to further acceleration in a way that ultimately creates an impassable barrier at light speed itself. When you push on an object to accelerate it, you're adding kinetic energy of motion. And at low speeds, this energy goes almost entirely into increasing velocity in the straightforward way we're familiar with from everyday experience. Push harder, move faster. Simple cause and effect. But as the object's speed approaches a significant fraction of light speed, something strange starts to happen. More and more of the energy you add goes into increasing the object's mass rather than its velocity, as if the universe is playing a cosmic shell game, redirecting your efforts away from speed and into inertia. This effect is negligible at everyday speeds, A car traveling at 100 kilometers per hour is more massive than when standing still, but only by about 1 part in 100 trillion, an increase so tiny that no conceivable scale could detect it. But at 90% of light speed, the object's mass has increased to more than double its rest mass, requiring more than twice as much force to produce the same acceleration it would experience at low speeds. At 99% of light speed, mass increases by a factor of 7. Every kilogram at rest now has the inertia of 7 kilograms, requiring 7 times as much energy to push it a little faster. At 99.9%, the factor becomes 22. At 99.99%, it's 70. The progression accelerates toward infinity as you get closer and closer to that ultimate speed limit. To actually reach 100%, to touch the speed of light itself with an object that has mass, would require infinite energy. More energy than exists in the entire observable universe. With its hundreds of billions of galaxies, each containing hundreds of billions of stars, not just a lot of energy. Not just impractical amounts of energy, but literally infinite. A mathematical impossibility, a limit written into the structure of space-time itself that cannot be overcome by any amount of technological advancement or clever engineering. This is profoundly different from other limits we encounter in everyday life, like the terminal velocity of a skydiver or the maximum speed of a car, which are practical limitations imposed by air resistance and engine power but could theoretically be exceeded with better design or stronger materials. The light speed limit isn't imposed by friction or engineering constraints. It's a fundamental property of how space, time, mass, and energy relate to each other. As unbreakable as the rules of logic themselves. Think of it this way. Trying to accelerate a massive object to light speed is like trying to count to infinity. No matter how long you count, no matter how much effort you expend, you can always add one more number, but you'll never actually reach infinity, because infinity isn't a number you can reach. It's a concept that describes something fundamentally unbounded. Similarly, you can keep pumping energy into an object, pushing it closer and closer to light speed. But each increment requires exponentially more energy than the last. And the final step to reach exactly light speed requires that impossible infinite energy, an endless expenditure that can never be completed. Only light itself can travel at light speed, and it can do so precisely because photons have no rest mass. They're pure energy, existing only in motion, never at rest, always racing through space at exactly the maximum speed the universe allows for any information or causal influence to propagate. If you could somehow catch a photon and bring it to rest, which quantum mechanics tells us is impossible, it would cease to exist entirely. Photons don't have a rest state. They're phenomena of motion itself, ripples in the electromagnetic field that only exist while moving at light speed. This is the iron law of relativity. Massless particles must always move at light speed. Massive particles can never reach light speed. And that difference creates a fundamental divide in the types of phenomena possible in our universe. But we still haven't answered the deepest question. Why does this limit exist at all? What is the speed of light actually measuring? The answer will transform everything you thought you understood about reality itself. Here's what generations of physics teachers have failed to emphasize. What gets lost in the mathematical formalism and the focus on photons and electromagnetic radiation. The speed of light has almost nothing to do with light itself. Despite the historical accident of that name, which makes it seem like we're talking about a property of a specific type of particle or wave, light, electromagnetic radiation, photons, whatever you want to call it, just happens to be massless, which means it travels at the maximum speed that anything in the universe can travel. A fundamental limit built into the geometric structure of space-time itself that would exist even continue, should in a universe without electromagnetism. Even in a reality with no such thing as light, what we call the speed of light is more accurately described as the speed of causality, the maximum rate at which cause can become effect, the universal limit on how fast information can propagate from one point in space to another, regardless of what carries that information. When the sun disappears, Earth doesn't immediately stop feeling its gravitational pull. The effect of the sun's absence, the change in the gravitational field, propagates outward at exactly the speed of light, taking 8 minutes to cross the distance and inform our planet that the cosmic rules have changed. During those 8 minutes, Earth continues orbiting a sun that no longer exists, following the gravitational instructions encoded in the field left behind, until the update arrives, traveling at light speed, and Earth suddenly finds itself in free fall, moving in a straight line tangent to its previous orbit. This isn't just true for gravity and light. It's true for every force, every interaction, every way that one part of the universe can influence another part, all operating at or below this maximum speed that we happen to first measure using visible light. The strong nuclear force that holds atomic nuclei together, the weak force responsible for radioactive decay, the electromagnetic force between charged particles. All of these influences propagate at exactly light speed, creating a cosmic speed limit for how quickly news of any change can spread through space. This is what the speed of light really measures, how fast reality can update itself, how quickly the universe can process cause into effect, the frame rate at which existence computes the next moment from the current moment. Think of the universe as a vast computational system, not a computer in the sense of circuits and silicon, but a physical system that processes information through the interactions of fields and particles. Each location in space, updating its state based on information received from neighboring regions. The speed of light is the maximum speed at which those updates can propagate, the limiting rate at which information about changes in one location can influence what happens in another location, creating a kind of cosmic bandwidth limit on how fast the universe can synchronize itself. Now here's why this matters. Why this speed limit isn't just an interesting physical fact, but a fundamental logical necessity for a coherent universe. If information could travel faster than light, if cause and effect could propagate instantly or faster than this limit, the very concepts of causality and time would break down in a way that makes rational comprehension impossible. Let me show you why through a thought experiment that reveals the deep connection between the speed of light and the arrow of time itself, between this apparently arbitrary speed limit and the logical structure of cause and effect. Imagine you're on Earth, and your friend is on a spaceship traveling away from Earth at 90% of the speed of light, moving so fast that relativistic effects are dramatic and unmistakable. You send them a faster-than-light message. Let's say it travels at twice the speed of light, instantly crossing the distance that normal light would take time to cover, delivering your greeting to their ship in half the time light would require. Your friend receives the message and immediately sends a faster-than-light reply, also traveling at twice light speed, bouncing your words back to you at this hypothetical superluminal velocity. Here's where it gets weird. Because of the relativity of simultaneity, because different observers moving relative to each other have different definitions of now and simultaneous, the sequence of events looks different from different reference frames in a way that creates an impossible paradox. From your friend's reference frame on that rapidly receding ship, their reply, sent immediately after receiving your message in their time, arrives back at Earth before you sent the original message in your time, creating a loop where effect precedes cause, where the reply exists before the question that prompted it. This isn't a quirk of perception or a measurement error. It's a genuine causal paradox, where the temporal order of events reverses, depending on your reference frame, where you could theoretically receive information about the future and use it to prevent the past events that caused that information to exist. You could send yourself a message saying, "Don't send the message," creating a logical contradiction that has no resolution. A universe eating its own tail in a loop of circular causality that makes no sense under any interpretation. The technical term for this is a closed time-like curve, a path through space-time that loops back on itself temporally, allowing an object or information to interact with its own past in a way that could create paradoxes, like the famous grandfather paradox, where you prevent your own existence. The speed of light limit prevents this, not through some arbitrary restriction imposed by physics, but through the deep mathematical relationship between space and time in special relativity, which ensures that anything moving slower than or at light speed cannot create these causal loops, no matter how you arrange your reference frames. The limit isn't there to frustrate our desires for faster-than-light travel or instantaneous communication across cosmic distances. It's there to preserve the logical consistency of cause and effect, to ensure that the universe has a coherent narrative where events follow from their causes in a way that doesn't create paradoxes or contradictions. Without this limit, without the cosmic censorship that prevents information from traveling faster than light, the concept of time as a one-way flow from past to future would break down, replaced by a tangled mess where past, present, and future blur together in ways that make it impossible to define what happens at all. Every interaction you've ever had, every cause that produced an effect, every moment where you made a choice and saw its consequences, all of this depends on information propagating at or below the speed of light, maintaining the arrow of time, preserving the logical structure that makes the universe comprehensible. The speed of light isn't a constraint that limits us. It's the foundation that makes us possible, the boundary condition that allows complex structures, like stars and planets and living beings, to exist in a universe that follows consistent rules from moment to moment. But there's yet another layer to this story, a quantum mechanical perspective that reveals why the speed of light limit emerges naturally from the mathematics of how particles behave at the deepest level of reality. In the early 1960s, the brilliant and iconoclastic physicist Richard Feynman, known as much for his bongo playing and safe cracking as for his revolutionary contributions to quantum theory, was giving a series of lectures at Caltech on quantum electrodynamics. The theory describing how light and matter interact at the quantum level with extraordinary precision. A student raised their hand and asked what seems like a straightforward question. When an electron travels from point A to point B, which path does it take? Does it follow the straight line, the shortest distance? Does it curve slightly due to some force? Which specific trajectory through space does the particle actually traverse during its journey? Feynman smiled, and his answer would change how we understand the quantum world and reveal something profound about why the speed of light is absolute. It takes all of them, he said, and then proceeded to describe one of the most beautiful and strange aspects of quantum mechanics that had emerged from his own work developing a new formulation of quantum theory. In the quantum world, Feynman explained through his path integral formulation of quantum mechanics, a particle doesn't choose a single path from start to finish. It simultaneously explores every conceivable path connecting those 2 points, including paths that seem bizarre or impossible by classical standards. The electron heading from your finger to a detector across the room doesn't just travel in a straight line like a thrown baseball. It simultaneously takes the direct route, curves left, curves right, spirals around, zigzags back and forth, loops out to the moon and back, travels through every point in the galaxy, even follows paths that would require moving faster than light. Every single path, no matter how convoluted or seemingly absurd, contributes to the electron's journey from source to destination, all of them existing in quantum superposition until the particle is detected and the path becomes actualized through measurement. But here's the crucial insight that Feynman developed into a complete mathematical framework. Each path doesn't contribute equally to the final probability of where and when the electron arrives. Instead, each path has associated with it a quantum phase, a kind of internal clock that rotates as the particle travels, with the rotation rate depending on the action along that path, a quantity from classical mechanics involving energy, time, and distance. For paths close to the classical trajectory, the one an object would follow according to Newton's laws or relativistic mechanics. These quantum phase clocks rotate relatively slowly and stay synchronized with each other, all pointing in roughly the same direction like a crowd of people clapping in rhythm. When you add up all these synchronized contributions, they reinforce each other constructively, building up a strong probability amplitude that makes the classical path the most likely outcome, which is why macroscopic objects appear to follow definite trajectories rather than spreading out in quantum fuzziness. But for paths that deviate significantly from the classical route, especially paths that would require moving faster than light or taking wildly circuitous routes through space, the quantum phase clocks rotate at wildly different rates, spinning out of synchronization like a crowd where everyone is clapping at different tempos. Some clocks point up, others point down, some left, some right, distributed randomly in all directions. And when you add up all these unsynchronized contributions, they cancel each other out through destructive interference. The same phenomenon that makes noise-cancelling headphones work by combining sound waves that are out of phase. The faster-than-light paths aren't forbidden in the sense of being ruled out by some cosmic law enforcement. They exist in the mathematics. They contribute to the path integral. The electron really does explore them in its quantum journey from A to B. But these superluminal paths interfere with themselves so destructively, their phases oscillating so chaotically compared to the near-classical paths, that their total contribution to the probability amplitude washes out to essentially zero, making them physically irrelevant, even though mathematically present. It's as if the universe computes all possibilities, including impossible ones, but then filters out the impossible through the mathematics of interference, leaving only the physically realizable outcomes with significant probability. The paths that respect the speed of light limit and the other constraints of relativistic physics. This is profoundly different from how we usually think about physical laws as prohibitions or restrictions. It's not that nature forbids faster than light travel and enforces that prohibition through some mechanism, but rather that the mathematics of quantum mechanics automatically ensures such paths contribute negligibly to real outcomes through the elegant mechanism of phase cancellation. The universe doesn't need cosmic police to enforce the speed limit. The limit enforces itself through the fundamental way quantum fields propagate, through the inherent mathematics of how probability amplitudes combine, through a self-consistent mathematical structure that allows only certain possibilities to survive the calculation and become observable reality. Feynman's insight showed that many of the apparent constraints and limits in physics, including the speed of light as an absolute maximum for information propagation, aren't arbitrary rules imposed from outside, but natural consequences of how quantum systems evolve, emerging from deeper mathematical principles rather than being fundamental in themselves. This path integral approach to quantum mechanics has proven incredibly powerful, allowing physicists to calculate with extraordinary precision how particles behave, how forces work, how the quantum world transitions to the classical world we experience at larger scales. It's been used to predict the magnetic moment of the electron to 11 decimal places, making it one of the most precisely tested predictions in all of science, verified by experiments that match theory to within a few parts per trillion. Every time these calculations work, Every time experiment confirms the predictions of quantum electrodynamics based on Feynman's formulation. We're seeing indirect evidence that this picture is correct. Particles really do explore all paths. And faster than light paths really do cancel themselves out through quantum interference. The speed of light emerges not as an external constraint, but as an internal consistency condition. A natural boundary that falls out of the mathematics, when you demand that quantum mechanics and special relativity both be true simultaneously. When you insist that the universe be both quantum and relativistic, and this brings us full circle to where we started, to that 8-minute delay between the sun's disappearance and Earth's awareness, which we can now understand as the time it takes for causality to propagate, for the quantum fields to update themselves across the distance, for information about the changed state of reality to spread at the maximum speed allowed by the self-consistent mathematics of quantum field theory in curved spacetime. So the universe has a speed limit, a maximum rate at which anything, information, causality, force, influence, can propagate from one location to another. A cosmic boundary written into the structure of space-time itself that nothing can exceed and only massless entities can even reach. This might seem, at first reflection, like a limitation, a restriction on what's possible, a cosmic frustration that prevents us from exploring distant stars in person, from communicating instantly across the galaxy, from accessing the vast majority of the universe that lies beyond our light horizon. And there's truth to that feeling. The speed of light does impose real constraints on what civilizations can do, how far they can expand, how quickly they can respond to distant threats or opportunities, creating a kind of cosmic isolation where each region of space is fundamentally alone, able to influence only its immediate neighborhood within the ever-expanding sphere defined by light travel time. But this perspective, focusing on what the limit prevents, misses something profound about what it enables, about why a universe with this particular speed limit might be the only kind of universe capable of supporting the complex structures and processes we call life. Intelligence, consciousness, a universe without the speed of light limit, where information could travel instantaneously or arbitrarily fast, would be a universe without causality in any meaningful sense, a reality where effects could precede their causes, where temporal order depended on arbitrary choices of reference frame, where the concept of what happens next became meaningless because next lost all coherent definition. In such a universe, there could be no persistent structures, no stable patterns, no entities that maintain their integrity over time, because the very notion of over time would dissolve into paradox, into causal loops and contradictions that prevent any coherent narrative from emerging. The speed of light limit isn't just some arbitrary number that happened to describe how fast photons move. It's the boundary condition that allows the universe to have history, to evolve from past to future in a way that builds complexity, that enables cause and effect to operate consistently enough that structures can form and persist and evolve into ever more sophisticated configurations. Every atom in your body, every chemical bond holding molecules together, every neural connection in your brain firing to create your thoughts. All of this depends on electromagnetic forces propagating at the speed of light, on causality operating at exactly this pace, neither faster nor slower. If light speed were significantly slower, the electromagnetic force would respond sluggishly to changes in charge configurations, making atoms unstable, preventing the rapid electron rearrangements that enable chemistry, shutting down the possibility of complex molecular structures that could encode and process information. If light speed were faster, approaching infinity, the universe would collapse back into that paradoxical state where causality breaks down, where quantum field theory predicts infinite energy fluctuations, where the mathematical framework describing reality generates nonsensical results that bear no relationship to anything we can observe or measure. The actual speed of light, 300,000 kilometers per second, emerges from deeper principles in quantum field theory and general relativity, from the fundamental constants that describe the strength of electromagnetic interactions and the geometry of space-time, all balanced in a way that permits stable matter, complex chemistry, stars that can shine steadily for billions of years, providing energy for evolution. This isn't to say our universe is fine-tuned for life in some mystical sense. It's simply to recognize that certain features of physics, including the existence and specific value of the cosmic speed limit, are prerequisites for the kind of complex information processing structures we associate with living beings and consciousness. We find ourselves in a universe with this particular speed limit not because the universe was designed for us, but because the kinds of observers capable of asking questions about the speed of light can only exist in universes where that speed limit exists and has a value conducive to complex structure formation. The anthropic principle, often misunderstood as invoking design or purpose, is really just a selection effect. We necessarily find ourselves in a universe compatible with our existence, just as fish necessarily find themselves in water rather than on dry land. Not because the ocean was created for fish, but because fish evolved in and are adapted to aquatic environments. Similarly, we find ourselves contemplating the speed of light in a universe where that speed limit makes contemplation possible, where causality flows consistently enough that brains can form, memories can persist, thoughts can lead to other thoughts in logical succession. The 8-minute delay between the sun's hypothetical disappearance and Earth's awareness takes on new meaning in this context. It's not a bug in the cosmic design, but a feature that ensures gravitational influences propagate causally, that changes in mass distributions don't instantly affect the entire universe, that local events remain local until their influence has time to spread at the maximum speed, consistent with preserving logical coherence. In a very real sense, the speed of light is the speed of time itself, the rate at which the universe computes the next moment from the current moment, processing the vast array of quantum fields and particle interactions that comprise reality into the continuous flow of experience we call existence. And we are part of that flow, patterns in those fields, information processing structures that emerged from billions of years of evolution under rules that include and depend on this fundamental speed limit. Our very consciousness, arising from electrochemical signals propagating through neural networks at speeds far below light speed, but governed by the same underlying physics. The limitation becomes liberation when you realize it's the foundation for everything you are, everything you experience, everything that makes existence coherent and comprehensible, rather than a meaningless blur of disconnected events with no causal structure. Right now, wherever you are as you listen to these words, you're sitting in a specific location in space, a particular point on Earth's surface that's rotating at about 1,600 kilometers per hour at the equator, slower near the poles. As our planet spins on its axis, completing a full rotation every 24 hours, and Earth itself is orbiting the Sun at approximately 30 kilometers per second, fast enough to circle the entire planet in less than 20 minutes, if that motion were along Earth's surface instead of through space, carrying you along in its annual journey around our local star. And the Sun, far from being stationary, is racing around the center of the Milky Way galaxy at roughly 250 kilometers per second, taking about 230 million years to complete one full orbit, meaning the last time Earth was in its current position relative to the galaxy center, dinosaurs were just beginning their long reign over terrestrial ecosystems, and the Milky Way itself is moving through space relative to the cosmic microwave background, the afterglow of the Big Bang, at approximately 600 kilometers per second. pulled by the gravitational influence of massive galaxy clusters in the direction of a region called the Great Attractor. Though that name overstates our understanding of what's actually there. Despite all this motion through space, at speeds that would seem impressive by any human standard, you feel none of it, sitting perfectly still in your own reference frame, experiencing no wind of motion, no sense of the cosmic speeds at which you're actually traveling relative to distant galaxies. And light from the sun takes 8 minutes to reach you. Light from the nearest star system takes over 4 years. Light from the center of our galaxy takes 26,000 years. And light from the most distant galaxies we can observe has been traveling for over 13 billion years. Starting its journey when the universe was young and our solar system didn't yet exist. Every photon that enters your eye right now, carrying visual information about the world around you, traveled at exactly 300,000 kilometers per second from its source to your retina. Whether that source is the screen in front of you centimeters away or a distant star light years across the cosmos, the GPS system in your phone or car is right now receiving signals from satellites orbiting overhead. And the software is automatically correcting for relativistic time dilation effects, adjusting for the fact that clocks on those satellites run 38 microseconds per day faster than clocks on the ground due to their motion and their position in Earth's gravitational field. Without these corrections based on Einstein's relativity, based on the fundamental connection between space, time, and the speed of light, your navigation would drift kilometers off course within hours, making the technology useless for its intended purpose of providing accurate location information. Cosmic rays from distant supernovae and other high-energy astronomical phenomena are constantly raining down on Earth's atmosphere, creating showers of particles, including those muons we discussed earlier. Particles experiencing such extreme time dilation that they travel 25 times farther than their brief lifetimes should allow before decaying into other particles. Hundreds of these muons pass through your body every second. Cosmic visitors that have traversed vast distances and experienced time differently than you do, though their passage is completely harmless. Just one of many invisible quantum processes happening constantly around and through you without any noticeable effect. The screen or device you're using right now to access this information, if it's electronic, contains semiconductors that exploit quantum mechanical effects. Transistors that work because electrons can tunnel through barriers they classically shouldn't be able to cross. Capacitors that store charge through fields propagating at light speed. All the fundamental physics we've been discussing manifested in practical technology you interact with daily without giving it a second thought. The food you ate today, the energy powering your body's cells, ultimately came from sunlight captured by plants through photosynthesis. A quantum mechanical process where chlorophyll molecules absorb photons and use that electromagnetic energy to drive chemical reactions that build sugars from carbon dioxide and water, converting mass and energy according to the same principles Einstein discovered. And that sunlight itself originated in the sun's core through nuclear fusion. The conversion of mass into energy following that famous equation, with each photon taking hundreds of thousands of years to random walk from the core to the surface through endless absorption and re-emission events before finally escaping into space and reaching Earth 8 minutes later. The very atoms comprising your body were forged in stars that lived and died billions of years ago. Massive suns that fused light elements into heavier ones through nucleosynthesis, then exploded as supernovae, scattering those atoms through space, where they eventually coalesced into new star systems, including our own, where some of them ended up in you. You are made of stardust, as Carl Sagan famously noted. But more than that, you are made of processes operating at the speed of causality, electromagnetic forces binding atoms into molecules, chemical reactions proceeding at rates determined by quantum mechanics. neural signals propagating through your brain at speeds governed by the same physics that sets the cosmic speed limit. The universe is not something separate from you, something you observe from the outside as a detached spectator. You are a pattern in that universe, a localized region of decreased entropy, a self-sustaining process that maintains its organization by consuming energy and expelling waste heat, operating according to the same fundamental laws that govern galaxies and photons. Your consciousness, your sense of experiencing this moment as now, emerges from the causal structure of space-time, from the fact that information propagates at finite speed, creating a light cone of past events that could have influenced your current state, and a light cone of future events that your current actions could potentially influence. The present moment, your subjective experience of now, is not a universal instant shared across the cosmos, but a local phenomenon, a particular slice through space-time defined by your motion and position, different from the now experienced by anyone moving relative to you or positioned at a different gravitational potential. This means that, in a very real sense, you are always alone in your present moment, occupying a unique position in the causal structure of the universe that no other observer exactly shares, though the differences are typically so small as to be practically irrelevant for human interactions. But for distant observers, those on other planets or in other galaxies, the concept of sharing a moment becomes truly meaningless. There is no frame-independent way to say what is happening right now on a planet orbiting a star in the Andromeda galaxy, because now depends on your reference frame, and there's no privileged perspective from which to make that determination. Yet despite this fundamental isolation, despite the finite speed of light, creating boundaries around what each observer can know and influence, we are connected through the causal web, through the fact that our past light cones overlap, that we share common causes in our history, even if our present moments don't align across cosmic distances. The photons from the sun that warmed your skin yesterday also warmed someone on the other side of the planet, though they experienced those photons at a different time in their local reference frame, creating a tenuous connection through shared past events. Even though your present moments exist in different slices of space-time, there could have been other universes, configurations of physical law different from our own, realities where the speed of light was different or didn't exist as a limit at all, where causality operated according to different rules, or perhaps didn't operate coherently in any way we would recognize as meaningful. In some of these hypothetical universes, information might travel instantly, allowing effects to propagate to arbitrarily distant locations without any time delay, creating a cosmos where every point knew immediately about changes at every other point in a kind of universal telepathic connection. In others, the speed limit might be much slower, light creeping across space at meters per second instead of hundreds of thousands of kilometers, creating a reality where the sky remained dark because photons from distant stars took so long to arrive that they would be absorbed by intervening matter before completing their journey. In still others, causality might work backward or sideways, or not at all. Effects preceding causes. Time flowing in multiple directions simultaneously. Every attempt to define a consistent sequence of events dissolving into paradox and contradiction, but we don't live in any of those universes, and perhaps couldn't, because the kinds of observers capable of contemplating the nature of reality require a universe with certain features, certain regularities, certain boundaries that make complexity possible. We live in a universe where the speed of light is 300,000 kilometers per second, where this particular value emerges from the fundamental constants describing electromagnetic interactions and space-time geometry, where causality propagates at exactly this pace, creating the arrow of time that allows history to unfold, patterns to persist, evolution to occur. This speed limit, which we've been exploring throughout this journey from Galileo's hilltop experiments to Feynman's quantum paths, is not an arbitrary restriction imposed by a cosmic lawgiver or a frustrating barrier that limits our potential for exploration and discovery. It is the foundation that makes everything else possible. The boundary condition that allows the universe to compute itself forward in time without collapsing into logical contradiction. The cosmic frame rate that ensures cause and effect maintain their relationship and meaning has a chance to emerge from the interactions of matter and energy. Without this limit, without the constraint that information and causal influence can spread only so fast through space, atoms couldn't form stable configurations because electromagnetic forces would operate instantaneously in ways that quantum mechanics says would create infinite energy fluctuations. Stars couldn't shine steadily for billions of years because the balance between gravitational collapse and radiation pressure would be disrupted if gravity propagated instantaneously rather than at light speed, eliminating the natural time delays that help stabilize stellar dynamics. Planets couldn't maintain stable orbits because gravitational interactions would no longer conserve energy and angular momentum in the way they do when gravitational waves propagate at light speed, carrying away excess energy from disturbed systems and allowing them to settle into equilibrium configurations. Life couldn't evolve because the chemistry of complex molecules depends on electromagnetic interactions proceeding at exactly the pace they do, with electron orbitals and chemical bonds forming through processes that require causality to operate at light speed, neither faster nor slower. Consciousness couldn't emerge because the information processing happening in brains requires neurons to maintain causal relationships, action potentials to propagate in consistent directions, memories to form through physical changes that persist, because the universe has a coherent arrow of time grounded in the light speed limit. You couldn't be here, listening to these words, contemplating the nature of reality, wondering about your place in the cosmos, because none of the prerequisites for your existence would be satisfied in a universe without this fundamental speed limit. The 8-minute delay we started with, that gap between the sun's hypothetical disappearance and Earth's awareness, represents something beautiful rather than frustrating when you understand it properly. It's the time required for causality to propagate, for the universe to update itself consistently, for changes in one location to influence other locations in a way that preserves the logical structure, making narrative possible. During those 8 minutes, you would still see the sun because the photons it emitted 8 minutes ago are just now reaching your eyes, carrying information about a past state, creating your present perception through the accumulated effect of countless particles that each traveled at the cosmic speed limit. And when darkness finally arrived, when the last photons emitted before the sun's disappearance completed their journey and no more followed, you would experience the transition not as a failure of the universe to warn you in time, but as the natural consequence of living in a reality where information has to travel, where news of distant events takes time to arrive, where causality operates at a finite pace. This is the universe we inhabit. The only kind of universe that could contain observers capable of understanding these principles, asking these questions, marveling at the elegant mathematical structure underlying the apparent complexity of physical phenomena. The speed of light is not a speed limit in the sense of something preventing us from going where we want to go or doing what we want to do. It's a fundamental parameter of reality itself, built into the geometric structure of space-time, emerging from the requirement that quantum mechanics and relativity both be true, manifesting in every interaction between particles and fields. It is the heartbeat of the universe, the rhythm at which reality processes cause into effect, the tempo at which existence unfolds from moment to moment. And we are part of that rhythm, patterns dancing to that cosmic beat, information processing structures that exist because this particular tempo allows us to persist. You began this journey wondering why the sun's disappearance would take 8 minutes to reach us, thinking perhaps it was an odd fact about light traveling at finite speed. Interesting, but not particularly profound. Now you understand that this delay reflects something far deeper, the fundamental causal structure of space-time. the maximum speed at which information can propagate, the boundary between logically consistent and paradoxical realities, the foundation enabling everything from atoms to stars to consciousness. The universe has a speed limit, and that limit is not a constraint but a gift, not a barrier but a foundation, not something keeping you small but something making you possible. And in understanding this, you've glimpsed one of the deepest truths about reality, that limits create rather than destroy, that boundaries enable rather than prevent, that the finite nature of the cosmos is precisely what allows for the infinite beauty of existence. The sun still shines, 8 minutes away. The universe still computes itself forward at the speed of light. And you are here, now, part of it all, made possible by the very limits that seem to constrain us.